Okay, let's get started. So the next hour and a half or so, hour and 20 minutes, we're just going to review a few things about what you see in a traditional kind of controls class and vibrations. Largely what we're going to be talking about for the next 2 days is going to be kind of vibration control problems. So we need to make sure we all have kind of the same vocabulary. Right? So one thing you're going to see, and you might have seen if you've taken a differential equations class or if you had controls already, is the Laplace transform. And the kind of full Laplace transform has this form for some kind of function f of t. Right? And what we can do is use this to solve differential equations, which is why you saw it in differential equations class, probably. In practice, we almost never solve this integral, actually, for most problems. Right? Kind of the shortcut, really, is to kind of, we're going to write s. It's kind of like taking the derivative and then kind of like the integral of something. Okay. This is really only true if I have zero initial conditions, as we'll see. Okay. So this is a shortcut we'll almost always use when dealing with Laplace transform from a controls perspective. Right? And if you're doing kind of pure differential equations and some more complex math, you're probably going to end up dealing with this one. But from a controls perspective, we can get by, particularly kind of baseline, undergraduate, introductory, graduate controls with just this kind of understanding. Right? So using that shortcut, let's kind of apply that over here. Right? So we had our equation of motion. And I'm just going to collect the terms a little bit differently. Kind of broke that equation out to collect all the x terms on one side of the equation, all the xd terms on the other. If I'm going to take the Laplace transform, I want to write the S-domain version of this equation of motion, as we might say. I can look, well, I can say, let's define x of s as the Laplace transform of x. Right? And we can do the same thing for xd. Okay. And now we can take the Laplace transform of this whole equation. And we can write, well, we have not one but two derivatives, so that's going to be like having s squared. And then we're going to have kd, and we have one derivative of x. So that's going to be our left side of that equation. And the right side of that equation follows something similar. What that lets me do, I can collect these terms. Now I have kind of the Laplace domain version or the S domain version of this equation of motion. Okay. So just to kind of walk through the steps again, so if we're going to follow this shortcut, for every derivative, I just multiply, put an s in its place. Right? So I have two derivatives there is like an s squared. Okay? One derivative here, just an s. Okay? No derivatives there, I just go from x to capital X, the Laplace domain. Okay, same thing on the right side. Okay, so this is kind of the Laplace domain version of that equation of motion. Okay, And then what I can do is I can think about this equation in a little bit different way, right, given this controller. I can think about, given some kind of input xd, what's the output x going to be? Okay. So I could write it like this. Something like that instead. Okay. And what this basically is writing is the ratio of output to input. Right? So given some kind of xd, what does x, the position of that mass, look like? Okay. Anybody know what this is called? Probably some of you. Well, yeah. What kind of equation is this? I think somebody said, yeah, transfer function, right? Yeah. This guy we call transfer function. How is the input transferred over to the output? Is one way to kind of think about that. Okay. So, what does this tell us? What can we think about? What does this information does this give us about our system? Well, what we can do is look at the kind of, I'm going to actually rewrite that. No, we don't have to worry about that anymore. Get rid of that. Have this already. Get rid of that. And let's get rid of that. Okay, so I'm going to just rewrite this on the other side of the board for now. Okay, so that's our transfer function for this system that we were working on. If we look at the numerator of that fraction, and we get the roots of that numerator, those are called zeros. Those are the zeros of this transfer function. Okay. The roots of the denominator are called poles. Okay, so you have every transfer function has zeros and poles. Okay? And what we're going to see in a few minutes is the location of those zeros and poles on the plot can tell us a lot of information about the system. That's why we'll look at it. Okay? You also see this denominator the denominator represents the characteristic equation, or the characteristic polynomial, if you're looking at just the denominator itself. Set it equal to 0, you get the characteristic equation. And it's called the characteristic equation because it tells us the character of the system, how it behaves. So zeros and poles, right? We set the characteristic, I guess strictly speaking, polynomial equal to 0. Find the the roots, we get the poles in the system. Okay. So we can plot those, let's say, for this particular system. most often you're going to have complex conjugate or complex poles and zeros. Right? So in this case, we have a pair of complex conjugate poles, and then we'll have 1, 0. So you'll see on this pole, pole 0 map or pole 0 plot, for this system, we have 2 poles, right? We have a second order polynomial and 1, 0. Right, so poles and zeros. Okay. Well, what good does that do us? Okay. Let's look at this in a little bit more detail. The location of these poles and zeros on this pole 0 map or pole 0 plot. Okay. I'm going to change out these terms a little bit. So remember we saw that this system was equal to this one? We saw those are the same. So instead of Kp and Kd, I'm going to write K and C. So thinking about it now that we have a physical spring and a physical damper there instead of a virtual one. Okay? Really no different mathematically, but I think might help us think about it more clearly. Okay. So we can write the same equation, just substituting terms. We can also take, and if we look back, let's do it this way. And substitute them one step further up the chain of these equations. Let's take and divide this by m. So multiply the whole thing by 1 over m. All right. And you'll see why I'm doing this in a second. Again, just divided the whole thing by m. Okay. And what this gets us to is a kind of unique form of this differential equation. Right? You have a differential equation in this form, second order ordinary differential equation, right? Where this first term has a unity or 1 out front. Right? You can say something special about these two terms. Okay? And what you can say that term in front of the constant is the natural frequency squared. And that term is 2 zeta omega n, which we'll talk about what these mean in just a second. Let me write out this form of the equation. Get an equation written in that form. Okay. So that's right. So we said omega n is natural frequency. What does that tell us about this system? Some spring damper thing, some flexible system. When we talk about its natural frequency, what are we really talking about? Talking about the vibration. What about the vibration? Oscillation. Something about its oscillation. What about its oscillation?
Motion that goes forward and back. And the repetitive manner.
That's right. So it's going to be, so this differential equation, right, we have a harmonic solution, right? If certain things happen with zeta. But in the general case, the cases that are interesting for a controls engineer, really, right, this thing's going to vibrate. So natural frequency just tells us the natural way the system vibrates. If there's nothing else pushing on it, and so we take and maybe hold XD still, and pull X, and then let it go, and it's going to vibrate back and forth. It's going to vibrate at the natural frequency. So if I pull on X and let it go, it's going to bounce back and forth at some frequency by itself. That's the natural frequency. It naturally wants to kind of oscillate at that frequency. Right? What does the damping ratio tell us? Anybody know? Right, so how quickly the vibration actually decays away, right? So in this case, if I don't have this damper, if I don't have C, if I just have the K, and I pull on it and let it go, how long does it oscillate? No damper now, just C, just K. I pull on M and let it go, how long does it bounce back and forth? Forever, yeah, if there's no damper there. And no friction, it vibrates forever. Right. I increase C a little bit. Now I add back the damper and I increase a little bit. It starts to decay out. Right. And I can keep increasing C and keep increasing C and get to some place where it doesn't vibrate. Right. Well, in the case, it doesn't actually stop. That's kind of one of the interesting things. So let's look at some 3 special cases, really. Well, we can also write just to make sure we have kind of completeness here. These 2 guys are actually equal. We're just rewriting the terms. So this solution to this differential equation actually has kind of three ways it can be solved, 3 cases of solution. And it depends on what the value of the damping ratio is. So if that damping ratio is greater than 1, we say the system is over-damped. Right? In an over-damped response, so let's say I'm holding XD, and I pull on X over to X0, and then let it go. An over-damped response then looks like what? Stops quickly, sure. Well, no oscillations is the big one, right? So it may not be quickly. Depends on how large zeta is. If zeta is really large, it could be slow, but it's not going to oscillate, is the big thing. So what this means really is that there's no oscillation. It doesn't necessarily mean it's fast. So you start at X, I pull it over to X0 and let it go, and it starts moving back to 0, but maybe not so fast. And it actually takes infinitely long to get there, to be true. But we get pretty close within a finite time. Okay. So smooth curve, decay towards 0. Okay. That's the overdamped case. Right. We have one case that's kind of similar. I'm going to put if zeta is equal to 1, we call that critically damped, or critical damping. Okay. And that also has no oscillation. But it's kind of the fastest you can go without any oscillation. Right? So maybe this is overdamped and maybe so zeta can be 1 exactly. So it's a little bit less, so it could be faster. But kind of same response, no oscillation. Okay. When might I want one of these responses? They're not fast, but there's no oscillation. So when might I want an overdamped or critically damped response from my system? Yeah, the next one we have is underdamped. So it turns out what I'm kind of getting to is quite often we want an underdamped solution, actually. But there are some cases where underdamped or overdamped might make some sense for a system. Any ideas when that might be? What kind of system you'd want to be overdamped? The other thing, maybe this will help. The other thing that no oscillation does for you is that in this case, it never goes past 0. It comes back. Right? So it never overshoots where you want it to be. Right? So if I pull it over to x0, it never goes less than its configuration. So in that case, there are some cases where that might make sense to have that kind of response. So for example, maybe a chemical process. Chemical process, sometimes if you go past your set point, you get into trouble. And we can avoid that by creating that. These kind of same equations can hold for some chemical processes, right? So we can kind of slowly approach the chemical process we need, right? Or maybe if you have some automatic door, right? You don't want it ever to go past where it latches, right? So you want it to kind of slowly close, a nice slow closing, right? So there's some cases where this critically damped, overdamped makes some sense. You're not really worried about it being really fast. It's more important that it doesn't go past and start oscillating. Right? So often we don't want these, but there are some cases where it might make sense to have an overdamped or critically damped system. Okay? So let's erase this. If we look at, let's look at the overdamped case on our pole 0 map. Look at just the poles. So the overdamped case has 2 poles on the real axis. So if you solve this out, we won't go through all the math to show this. But just know if you have two poles on the real axis like this, and that's all you have anywhere else, you might have a 0 too, then you're going to have a critical damp case, right? Or overdamped case. If you look at the critically damped case, you actually have repeated real poles, repeated roots. So these are actually at the exact same location, right? But they're still both completely on the real axis. Okay. Our kind of last case, which we said was underdamped. Okay. And underdamped, if these are not oscillatory, then underdamped is oscillatory. Right? It's kind of the opposite of that. So we have some oscillatory response. So in the case of our example over there, we have started some x0 now, pull our mass over, and now it's going to oscillate back and forth. And how long it oscillates and how quickly that decays, it still depends on zeta. Right. So we could have some response Let's plot a few of these actually. So we've said before, if zeta is 0, then this thing would oscillate forever. Okay. So let's look at that case. So if I have zeta 0, it just oscillates forever. Back and forth and back and forth and back and forth forever. Right? This is actually a special case of underdamped. And we'll call that undamped. There's no damping at all if zeta is 0. Okay. If we increase our damping a little bit, what happens to this response? It starts decaying. Right. So I'm actually going to draw that on a separate plot. Well, let's draw one here. So we start at the same place. The frequency is mostly the same. Each cycle we're getting a little bit smaller. That's going to be 0.1 or something. So we still have pretty low damping. It doesn't take a whole lot of damping before you start decaying pretty quickly. Okay. Okay. And what's a little bit cool about this, we can let's look at that response again. Start at x0. Let me just draw that one more time. Is that we can look at the envelope that defines how quickly we're decaying. So we can look at this. And we see our response stays between those two curves always. What kind of shape is that? Any guesses? What's that decay envelope look like? Not quite. It's actually just an exponential. Yeah, there you go. So we have exponential decay when we have an underdamped response. And what that looks like, those decay envelopes look like that, top and bottom. So e to the minus zeta omega n t defines that decay envelope. Okay. And that's true for all these underdamped responses. So you can see here, the higher that zeta is, the faster that the decay's envelope is going to go to 0, which means that response decays towards 0 more quickly. Okay? If we look at our pole 0 map for this case, we can get a lot of information about this plot just by looking at, so for these underdamped cases, if you have a set of underdamped poles, they're going to be complex conjugates. Right? So you're going to have some component, some real component, some imaginary component. And you'll have a complex conjugate pair of poles for the system. And you can tell a lot by if somebody just showed you this pole 0 map of a system, you know a lot about its response immediately from this. And what you know is actually the length of this vector from the origin to that guy gives you the natural frequency. Okay. So if you get this value, you have the natural frequency in radians a second. Okay. We know right away that the real component of these guys is zeta omega n. So if we go over, we got zeta omega n there. Okay. We know right away the imaginary component is omega d, the damped natural frequency omega n 1 minus zeta squared. Okay. And then we also know something about that angle. We measure that angle, we know that angle is related to the damping ratio. Right? So if you give me just a pole zero map, right, and it has complex conjugate pair of poles on it, I know immediately what its natural frequency is. I know immediately what the damping ratio is and how quickly it's going to decay. Right? So by looking at these pole zero maps, we can tell a lot of information about our system. Right? And we're not going to talk really about the root locus in these 3 days. That's effectively what the root locus is setting up. It's showing you how the location of these poles change as you're changing your gains. And therefore how the natural frequency and damping ratio change as your pole location changes. Okay. Okay, so simple transfer functions. Let's work one quick, easy example to make sure we understand that. So let me erase this part. Okay, so let's just take a simple system, one we'll talk about a little bit more, something similar to this, and write a transfer function. So we have some. So we have some mass, some point mass M at the end of a massless rigid rod of length L. Okay, so pendulum, really simple little system, right? And then we have some torque about that pen T. Okay. Simple systems, masses and springs and pendulums you can do a ton with if you understand them really well. And they give us a lot of understanding. Okay, so let's take, and I'm going to define some set of axes x to the right out here, y up. And let's define that pen as point O. There. Okay. If I'm going to write the equation of motion for the system, what's the first step? I'm going to do this, and I really push on my students to always do this. And it's my recommendation for you to always draw a free body diagram, even for the really simple systems. Just always be in the habit of drawing free body diagrams, right? So for our system, okay, what kind of forces do we have on our free body diagram? Gravity. So we have gravity acting where? Just on the mass, right? The rod's massless, so gravity is only acting on that one. What else do we have? We have the tension in the pendulum. Yes, if you're thinking about it as a string, sure. If it's a massless rigid rod, then you can kind of make some assumptions about the internal tension there that simplify this a little bit. And what that does, basically, any kind of that internal tension, because this is massless and rigid, it's basically grouped in with the reaction forces at the pen. Right. So we know in some case we have some unknown reactions at that pen that hold that pen in place. Right. What else do we have? We have one more. Yeah, the applied torque. That's right. Okay. So I think that's what we have. There's a nice little free body diagram for this system. Right. So what's next? What's that? Equation. Okay. What equation am I going to use to write the equations of motion? So what's a little bit unique about this system, makes it kind of easy for us, is that it's in what we say pure rotation. Right? So it's just rotating about 0.0. So we can use that kind of simplified form of kind of equation of motion, if you will, right? That's in pure rotation. Right? So we can say, and we know it's in pure rotation about 0.0, we could say that, right, since it's in pure rotation. Okay. So let's look at the sum of the moments about 0.0 part of this equation first. Right. So what do we have? We have T first, that's the easy one. And that's in the positive K direction. And then what do we have? Some kind of moment from gravity, right? And this will always work for you. R cross F, right? You can get those moments. Let me do that. Does that make sense for our system? Physical sense. Yes? Yeah, it should, right? We have some positive torque. It's trying to make theta bigger, so it's positive. Gravity is always going to try to make theta smaller, right? So we have a negative sign there. And then everything's in the positive K direction, right? We have a planar system. Everything better stay in that K direction if it's going to stay in this plane. So it makes intuitive sense. And that's another check you always want to do when you're developing an equation of motion, is think about, do these equations really make sense for the physical system I'm trying to describe? Okay, so that's the sum of the moments part of it. What's the change in angular momentum?